All right, you are welcome to today's lecture. Today we'll be looking at the relationship between coefficient of expansion, or sometimes some textbooks call this as coefficient of cubic expansion, and compressibility denoted by A. All right, so for us to establish the relationship between these two, we are going to go back into uh, cyclic relation, that is relating volume, pressure, and temperature. We've already established this relationship from our first video, so you can watch that how we come about this. All right, so you are going to recall carefully that the partial derivation of P all over the partial derivation of T, keeping V constant, into the partial derivation of T, partial derivation of T, all over the partial derivation of V, keeping P constant, into the partial derivation of V, all over the partial derivation of P, keeping T constant. Everything is equal to what? Minus 1. All right. And you are also going to recall carefully that the thermal coefficient of cubic expansion denoted by B is equals to 1 all over V into the partial differentiation of V all over the partial differentiation of T, keeping P constant. And as well, we are going to recall carefully that K, which is our compressibility, is nothing but the minus 1 all over V into the partial differentiation of V all over the partial differentiation of P, keeping T constant. All right, so from we are going to be using these three equations to be establishing the relationship between uh, coefficient of expansion and compressibility. All right, so let's call this equation number 1, and let's call this equation number 2, let's call this equation number 3. All right, from equation number 2, I'm going to make the partial differentiation of V all over the partial differentiation of T, keeping P constant, the subject here. So if I do that, I'm going to have the partial differentiation of V all over the partial differentiation of T, keeping P constant, to be equals to beta V. All right, let's call this equation number 4. All right, so from equation number 3, I'm going to be making partial differentiation of V all over the partial differentiation of P, keeping T constant, the subject. So I'm going to have this as the partial differentiation of V all over the partial differentiation of P, keeping T constant, to be equal to minus K P, equation number 5. All right, so a quick one. We are going to be substituting uh, equation 4 and equation 5 into equation 1. All right, because from equation 1, we have partial differentiation of P all over the partial differentiation of T, keeping V constant. So the partial differentiation of P all over the partial differentiation of T, keeping V constant. And here we are having the partial differentiation of T all over the partial differentiation of V, all into what? Into P. Now, before I proceed, let's make this the subject of formula from here. If we make this the subject here, it means we are going to divide through by this and this. We are going to divide both sides by this and this, and which is going to be equals to minus 1 all over what? All over the partial differentiation of T all over the partial differentiation of V, keeping P constant, into the partial differentiation of V all over the partial differentiation of P, keeping T constant. All right, so now the next thing we are going to do is we are going to take the inverse of this, so as everything here will go back up. So which is the partial differentiation of P all over the partial differentiation of T, keeping V constant, will be equals to the partial differentiation of V all over the partial differentiation of T, keeping P constant, into the partial differentiation of P all over the partial differentiation of P, keeping T constant. So this is what we are going to get now. All right, now we can therefore make our substitution now. We are going to substitute equation 4 into and equation 5 into this equation. Let's call this equation is still our equation 1. No, it's from equation 1 we just deduce this. So let's make this equation star. Let's call this equation star. All right. Now you will discover that we already established that the partial differentiation of b all over the partial differentiation of t, keeping p constant, to be equals to what? Beta v, of course, which is here in our equation. So we are going to replace the partial differentiation of v all over partial differentiation of t, keeping p constant here with what? Beta v. So it shows that this is going to be equals to the partial differentiation of p all over the partial differentiation of t, keeping v constant, to be equals to beta v multiplied by. All right. Now here we have the partial differentiation of p all over the partial differentiation of v, keeping t constant. So let's check equation 5. You see in equation 5 we are having the partial differentiation of v all over the partial differentiation of p. But here we are having the partial differentiation of p all over the partial differentiation of what? V. So it means we are having the inverse of this here. So how can we make what is here to be exactly as this? Means we are going to take the inverse of this. So by taking the inverse of this equation number 5, we are going to have the partial differentiation of p all over the partial differentiation of p to give us 1 all over this. That is what I'm saying next test is this. If we have the partial differentiation of p all over the partial differentiation of p, keeping t constant, to be equals to minus kv. So if I take the inverse, that is, if I take the inverse, that is 1 all over partial differentiation of b all over partial differentiation of p, keeping t constant, to be equals to 1 all over minus kv. So now you can therefore from Bodmer's now, this will go up, this will come down. Then we are going to have this as the partial differentiation of p all over the partial differentiation of b, keeping t constant, to be equals to 1 minus 1 all over kv. So now, which is just the same thing as what is here now. So it shows that we are going to be substituting minus 1 all over kv for partial differentiation of p all over partial differentiation of v, keeping t constant in our equation star. So I can rub this off now. All right, so we are going to substitute minus 1 all over kv here. All right, and you will notice that, oh sorry, there is a little mistake here. By the time we make the p all over the t the subject here, don't forget we are having minus 1 all over this. So when we invert it, when we take the inverse, there will be a negative sign here. So by the time we substitute for this here, the negative sign will still remain. So sorry for that. All right. So negative will multiply negative. This negative sign will cancel out. Then v will cancel out. Then we'll be left with, we say, the partial differentiation of p all over the partial differentiation of t, keeping v constant, to be equals to beta all over what? All over k. And here is the relationship between beta and what? And k. But here is the relationship which is correct. So for further modification, when the equation of state is known, let me write this. When equation when the equation beta and k, that is coefficient of expansion and compressibility, can be found by differentiation. Be found by differentiation. Be found by differentiation. Let's take an example for example now. Let's take for a gas let's take for a perfect gas. For a perfect gas, all right. So we are considering a perfect gas as an example here. When the equation of state is known, the, we can the value of this can be found by differentiation. All right, we know that from perfect gas, PV is equals to what? RT. So from perfect gas, set PV is equals to RT, right? Now, by making V the subject here, we make V the subject, V will be equals to RT all over what? All over P. All right. So if V is equals to RT all over V now, so now the thing we want to do here is we are going to differentiate V in respect to T, keeping P constant. All right. We are going to differentiate V in respect to temperature, keeping P constant. All right. So how do we do this? If we want to differentiate, that is the partial differentiation of V in respect to T. So it means that here we are going to be having R all over P to be constant. Then it's going to be the partial differentiation of T all over the partial differentiation of T, keeping P constant. All right. So now you agree with me that this will cancel out this to give us 1. Then the differentiation of this, the partial differentiation of B all over the partial differentiation of T, will, keeping P constant, will be equals to R all over what? P. All right. So now the next thing we are going to do is we are going to differentiate V in respect to P, keeping T constant. We established that V is equals to RT over P. So now we want to differentiate volume now in respect to pressure, keeping temperature constant. So we are going to say partial differentiation of volume all over the partial differentiation of pressure, keeping temperature constant. All right. So now here we are having RT. We'll be having RT as a constant value. So we'll factor it out. I'm going to have RT. Then it's going to be the differentiation of volume. The differentiation of volume, that is, we are taking the differentiation of this in respect to pressure into 1 all over what? T. So we are differentiating this. All right. And we know from differentiation that or from the laws of indices rather, that we can rewrite this as T to the power of -1. Sorry, is it T or P? Sorry, it's P. All right. So now we can write this as P to the -1. All right. So if we differentiate this now, we are going to have this as RT. If we differentiate this, we are subtracting 1 from this. That is -1 minus 1 is going to give us what? -2. So it's going to be P to the power of -2. So which we can write as RT all over what? All over P squared. All right. So it shows that partial differentiation of V all over the partial differentiation of P, keeping T constant, is going to give us this. All right. We've established this. Let's call this one equation 1 prime, and let's call this equation 2 and like this. All right. So now let me rewrite this equation, this equation there, and this equation here up. So we are going to have partial differentiation of V all over the partial differentiation of T, keeping P constant, will be equals to R all over what? P equation is. Then this one is going to give us partial differentiation of V all over the partial differentiation of P, keeping T constant, will be equals to RT all over what? All over P squared. All right. Now, you are going to recall carefully now. We want to relate this now to uh, coefficient of expansion and compressibility. All right, we just stated that our compressibility, let me start with coefficient of expansion, B, is equals to 1 all over B, 1 all over B into what? The partial differentiation of B, partial differentiation of B, all over the partial differentiation of T, keeping P constant. And then we also state that K is equals to minus 1 over B into the partial differentiation of B, partial differentiation of B all over the partial differentiation of P, keeping T constant. All right. Now, look at this equation here now. We already have partial differentiation of V over the P, that is partial differentiation of B all over partial differentiation of T, keeping P constant in this equation here. So now we can replace this with R over P, and then we can replace what is here with what? RT over what? P squared. So now beta, which is now as a coefficient of cubic expansion, will be equals to 1 all over B into R over P, R over P, R over P. So which is equals to R all over what? BP. All right. R all over what? BP. So we can therefore say our beta here is equals to R all over what? BP. All right. So let's leave this for now. All right. Again, let's substitute for K. If we make substitution for K, what are we going to get? Make substitution for K. K is equals to, we have minus 1 all over B into partial differentiation of V all over partial differentiation of P, keeping T constant, is RT all over what? RT all over P squared. RT all over P squared, which is going to give us what? Which is going to give us minus RT all over P squared. All right. So if I can write this as K is equals to minus RT all over what? The P squared. All right, so let's clean this part. So now, let me rewrite what we get for beta and K. Then beta is equals to R all over BP. And we said K equals to minus RT all over BP squared. All right. So now from here, I know that from PV, from ID gas or from perfect gas, we know that PV is equals to RT. All right. So if I decide to bring out R all over VP from here, R all over VP, that is, I'm going to divide both sides by VPT. So here, if I divide both sides by VPT, VP, PVT, R all over PVT. So now this will cancel out this here, and T will cancel out T here. So we'll be left with 1 all over T to be equals to R all over what? PV. So from here now, I can R all over VP, which is here, which is equal to 1 over T. So we can rewrite our beta to be equals to 1 all over what? T. So our coefficient of cubic expansion, coefficient of uh, expansion is inversely proportional to what? Is inversely proportional with what? Temperature. So this is another relationship between cubic expansion and temperature. That is, as our cubic expansion increases, what happens to temperature? It reduces. As our temperature increases, cubic expansion what? Reduces. All right. So now let's try to bring out a relation for this. Let's try to bring out a relation for this. All right. So from here I can also bring out if I bring out ROT. Let's try to all right. So we have established the relationship between beta and C. So let's make from PV equals to RT. Let's try and make P the subject. Let's try and make P the subject, but let me just try it out. All right. So we have a K. We said from there we have K to be equals to minus RT all over VP squared, right? So we can bring out P from here. From let's go to PV diagram. Sorry, not PV diagram. PV equals to ROT. All right. So now this is ROT V. ROT, if I divide both sides by V, I'm going to get P to be equals to ROT all over what? V, right? Now, since I am having ROTV here, I can replace this ROTV with what? P. And for me to do that, means that K here, K will be equals to, if I bring a negative ROT all over P multiplied by 1 all over what? P squared. All right. So now if I do this now, K now will be equals to ROTV is P. So we are going to have minus P multiplied by 1 all over what? P squared. Then this P now we cancel out 1P here. Then K will be equals to minus 1 over P. So this is another relationship between compressibility and what? And pressure. So if you are asked to show the relationship between cubic expansion, this is it here. They also has to show the relationship between uh, compressibility and pressure. This is it here. And we've also established relationship between uh, coefficient of expansion and what? Compressibility.